Hello, welcome. My name is Ian. In this video, I want to discuss the topic of estimators. So often we have a system with some kind of population. And if we recall back to the earlier videos, we remember that this population is the space of all possible outcomes or events. So in the example of the dice throw, this was going to be enumerating all the different results that you could get if it's two dice. Remember, there are 36 possibilities. And this population has, for example, a mean value. So if we wanted to know the mean of the two dice throw, we would go through all of the possible events that you get. You could get a net 7, net 8. We would count these up and be able to compute a mean for this kind of ideal population. And this distribution also has a particular spread. So, you can do the same. We could compute a sigma for a probability distribution. But in a lot of situations, we don't have access. So this might be an experimental setup where the population is a physical process that is extremely complex maybe. And what we're doing is we're taking measurements, knowing that this is sampling and this population, or maybe we're using the Monte Carlo method. We're using a random number generator to sample this population, having reproduced the generating mechanism for the process. But in either case, what we're going to be left with is some sample information. So we have a sample mean that we took from our measurements, and we also have a standard deviation of our sample. And we talked earlier about confidence intervals. And in those cases, we were using like a reported instrument standard deviation. We said the mass balance has a known precision of, say, 0.01 grams. And then we could take it from there. If we wanted to, we could compute the standard error of the mean for our mean values and create confidence intervals, reflecting the fact that we took multiple measurements. But all of these were still calculated. If you remember the formula we used for this, it was sigma over square root of n. We're still using the sigma, and that sigma, this standard deviation, was a known population sigma, coming from possessing this a priori information already about the population. And in many cases, we simply don't have access to this. And the question is, what can we say about the true mean and the true standard deviation, given that we only know the sample mean and the sample standard deviation? And so this brings us to the topic of estimators. And we can kind of create sort of generic version of an estimator. And usually we'll use this notation, the hat here, to denote that we're using an estimator. And this is in contrast to, say, the value without a hat, which would be maybe the population. So in this case, we're saying that a hat, this is an estimator of the true A, whatever it is. And A is going to be some statistic, maybe it's the population skew, or maybe it's the population variance, or the mean. So what are estimators? So in turns out you can have many different definitions of estimators. So question is not so much what is the estimator? It's more a question of which estimators should we use, and which ones are good and which ones are bad. And so a good estimator possesses these three criteria. It should be consistent. So this means that the difference between the true value and the estimator, it should average out. It should disappear when we go to large n, when we take many measurements. Or another way of saying this is that the limit of a hat as n goes to infinity should be a, the population A. The second criteria is related to bias. So the average, the mean of a hat, it should be the same as the true A. Or another way of stating this is that the expected value or the expectation of A hat should be equal to A. So if we do multiple rounds of our estimator, then the average, the population average of A hat should be exactly equal to the true value of A. And then finally, efficiency. And this is kind of a statement about the spread of our estimator. So we want the variance of A hat to be as small as possible. In other words, we want A hat to be as close to A on average as possible. If A hat is tightly clustered around A, then any given round where we're producing this estimator is likely to be quite close to the real one. Whereas if it's very spread out, then our estimator is likely to be off, and then we'll have misinterpretation of the population in that case. And so we can have, say, a population of cell areas here, and what we're wondering about is what is mu? What does the population mean? And what we've done is we've taken n area measurements. So we've sampled from this population. We have x1, x2, all the way up to x sub n. And we are trying to figure out what mu could be. And so we have different possible estimators that we could use here. So here we have, in this column, we're going to propose different definitions of an estimator for mu, a mu hat. And we're going to examine the criteria that we discussed in the previous slide to see whether this is a good estimator or a bad estimator. And so one example would be we can add up the areas and divide by n. So this would be, of course, the sample mean, and we can examine these. So this is the limit of a hat as n approaches infinity equal a. Indeed, that is the case. If we were going to take more measurements here, then, of course, our sample mean is going to approach the true mean. This is, of course, the law of large numbers that we explored previously. What about the bias? So is the expected value of a hat equal to a in this case, or is the expected value is the mean of our means going to equal the population mean? Well, that is also true. And then how about the variance in this case? So we have the variance of the mean. We discussed this when we were talking about standard error of the mean. The mean itself is a random variable, and it is relatively tightly distributed depending on your value of n. Okay, so that's kind of an obvious example, but we could have other estimators of mu hat. So another example could be we add up the first 10 areas only, and then divide by 10. So instead of taking all n in this case, we're only taking the first 10. And so a problem we're going to have here immediately is that as n goes to infinity, we're not going to approach the true value here, because in all of these cases, we're still only taking the first 10. So that's true whether or not we have, n equals 1 million or n equals 1 billion, we're still only just taking the first 10 areas and divided by 10. So this is going to violate our first criterion here. So this is a bad estimator. And in this case also, this means we're also doomed to have a relatively broad distribution of means that we're going to get because we're not we're not influencing the value that we get as we go up in n the way we do with the sample mean. How about another definition? So we could assign a value of 80 micrometer square regardless of x. This is kind of a joke, I guess, but basically anything can be an estimator And the question is, how good is it or how bad is it? In this case, of course, increasing n is going to have no effect on the value we get. The expected value of this estimator has nothing to do with the true value, so it is not unbiased. It is in fact very biased. And then, the variance actually is going to be really small in this case, but well, yeah, you're not getting any information about the true value in this case. Okay, and then let's consider another definition here. What if we add up all the areas and divide by n minus 1? So this is going to get better when we have large numbers of n. It is going to start to approach the true value. But in this case, we've introduced a bias. Since we're not dividing by n, we're dividing by n minus 1. The mean here is going to be systematically off. And of course, it's going to matter less and less as n goes to infinity. But nevertheless, the expected value of a hat, in this case, is not quite the same as the population A. Right. So yeah, and we can compute this here. So the expected value in this case, we can compute it directly. N times mu over n minus 1. This is not equal to mu. If we go and evaluate the expectation value for this formula. So here are some interesting estimators that may arise. So we already discussed this mu hat, an estimator for mu, an estimator for mu that you can use is the sample mean. And it satisfies the first two criteria. And then for the third one, it also satisfies this, and we explored this, right? So it has this standard error, the mean, that we can use to describe the spread of the sample mean itself. And then that is going to get better and better the larger n is. What about the variance? So we have a population variance out there. So v hat is going to be our estimator for that true population variance. And suppose we used the most obvious definition. So what if we just take the definition of the variance, but instead of mu, we're going to use our x bar here. So basically, we're taking the sample variance. So is the sample variance equal to is the sample variance a good population estimator or a good estimator for population variance? And what's interesting is, it turns out this is actually subject to a bias. So the expected value, or the mean v hat in this case, actually is not equal to the population v. And this has been proven and shown. And instead, it's equal to this quantity here. And then this can actually be used to as the basis for creating a corrected version of v hat. And so that brings us to this s squared here. So you often see this notation here. So s squared then is the unbiased estimator for the population variance. And the only difference is we've divided by n minus 1 here. And then this removes the bias that you get. And then people have figured this out. So the variance of this variance estimator here follows this rule here. And so this is also relatively efficient in terms of spread. Okay, what about the standard deviation in that case? So in this case, we actually do have also a bias for standard deviation if we just take the square root of this s squared here, the unbiased estimator. But in most cases, this is what is done anyway. And so typically what is done is, this biased estimator for the population sigma is used because the bias is not so bad. And then the spread of this estimator is itself subject to some some variation that follows this trend here. And then just throwing in another one of these here. So we have an estimator for the correlation as well. And so people have derived or come up with an unbiased estimator, again, involving an n-1 quantity here that you can use to, without bias, compute an estimate for the population correlation if you have two sets of paired data. And then we also have a variance of this estimator that has this quantity here. Okay, so what do we need to be able to report using estimators? So we have some sort of population. We have a sample that we've taken from that population, X1, X2, etc. And we want to make a confidence statement, ideally about the population. So we go ahead and we use our estimator. So we have, say, our estimator for sigma. So we use this definition. We go back here. We can use this definition here, S or sigma hat. And that itself is subject to some sigma, which again, we have here, if we go back to this table. So the variance of sigma itself has its own descriptor here, or the sigma of sigma hat has this description here. And so if we want to make a confidence statement about sigma, or about the population standard deviation, then we can do so using our knowledge of the variation of the estimator itself. So we can make a 68% confidence statement, that the true standard deviation has this value, our estimator, and plus or minus this variation here, or the sigma of sigma. So we can do the same thing for the mean, maybe a bit less confusing. We have a sample mean here, right, x bar, and then we can use our standard error of the mean. But in this case, we're going to substitute sigma, since we don't know it, with sigma hat, our estimator. And in that case, we're using this definition here, the square root of this unbiased variance estimator. And so how would we report this? What would this look like? So we would report x bar here, plus or minus our standard error of the mean estimator, our estimated standard error of the mean. Right, and note that this is different from the situation where we know sigma a priori, right? So if you have a mass balance and the manufacturers have reported a precision, an error, then you don't need to do this. But in a case where we don't know that information, we've taken a sample and we've computed a sample standard deviation, then we will want to use these estimators instead and report it using the correct convention here. Right, so this is just sort of a comparison. So we had this case, right, with the mass balance, and then we might say that the manufacturers reported to us that the precision of the balance is 0.1 grams. And if we take a measurement and we weigh some stuff, we say that's 0.086. So this confidence statement here is like saying with 68% probability, the true mass lies within the interval of 0.086 minus 0.1 grams and 0.086 plus 0.1 grams. And the thing about this confidence statement was it was based on assumption that the errors follow a Gaussian distribution. So we had the Gaussian distribution, and to simplify things, we can use the Z score, right? And this was basically a way to just have a unit Gaussian where we think in terms of standard deviations away from the mean. So if Z was 1, then it means we're within 1 standard deviation of the mean. If it's -2, then we're 2 standard deviations to the left of the mean. And that was for one measurement, but then we have a corresponding one for multiple measurements with the SEM, and then it's basically the same thing, except instead of X, we have Z defined in terms of X bar here, the sample mean. Okay, so that's all fine. But what if we don't know sigma? So again, we're using measurements that we've taken. We have data, and we have a computed estimator for the standard deviation, sigma hat, or again, we're using S to denote this. And we want to make a confidence statement, but we have a problem. The parameter for the Gaussian distribution is the population standard deviation, right? This is a requirement to use the Gaussian distribution, but we don't have the population standard deviation. It's unknown. What we have instead is the estimator, our computed sample S here. And in this case, we then need to use a different distribution. So we have to use what's called the student's T distribution. And this takes as its parameter our estimator, sigma hat here. And that allows us then to produce confidence statements like we did in the case of the Gaussian distribution with a known standard deviation. And we have a very similar table, the t-test table, that we can use in the same way we use the Gaussian integral table. And there's one extra kind of addition here. So in the student's t-test table, we have this idea of degrees of freedom, or df. And so this is going to be n minus 1. So our sample number of samples we took minus 1 is going to give us a df value. And depending on your df value, you're going to look up different values. So here we have, going down in this column, values of df, 1, 2, 3, 4, etc. And that's going to influence what area you're computing. So if we want a 95% confidence, for example, here, depending on df, this is going to give us the number of standard deviations that we need to use then for 95% confidence. So instead of Z, we have T here. Instead of thinking of standard deviations away from the mean in the Gaussian, we're thinking of standard deviations away from the mean in the T distribution, and we're computing these values using this estimator sigma hat here. So here's an example. So we have the blood insulin levels of 25 healthy patients, and they show an average fasting concentration of 128. And this is with a standard deviation estimate of 15 picomoles per liter. And I want to know, what is the confidence limit of the population mean insulin level? So we want to be able to produce a confidence statement about the population, because of course that's what we're interested in. But the only thing we have access to is our measurements. And so using our measurements, we're able to get a sample mean, 128, and we're able to compute the estimator for the standard deviation, right, using the formula we showed earlier. And we know that n is 25. We took 25 samples. So we can use our formula for the SEM, but substitute our estimator in there instead of the population standard deviation. So we can compute this value. We get a value of 3. And now if this were a Gaussian example, right, if this were a case where we knew the standard deviation of the population, then we could just go into the Gaussian table and look up, what's 95%, or, we already remember it basically. So we know that 95% is 1.96 standard deviations away from the mean. So we could create this confidence interval straight off the bat. and we would give, an answer like this. The range is between 122.1 to 133.9 with 95% probability, 0.95 probability. But since we don't have that population standard deviation, we only have the estimator, then we're going to use instead the t-distribution. And so we need to look up the correct value of t, the t statistic, but for the correct number of degrees of freedom. And so we can compute that, right? It's just n minus 1, so 25 minus 1, or 24. So we're going to be in this row here. And we want 95% confidence. So we have that, we know that that's going to be this column here. And then for the two-tailed case, we're using the two-tailed table, we have 0.05 here for two tails. So we get a t statistic of 2.064 in this case. And so that means that 2.06 times our estimator, in this case 3, is going to define the range in which 95% of in 95% of universes will be correct if we say that the population mean lies within this range. So in this case, we take the mean that we got, 128 minus 2.06, so that's 121.8, and then that 2.06 times 3 here. So then that minus our mean, 128 minus that value, and then plus that value is going to define this range here. So in 95% of universes, the true mean lies within this range. And that's the population that we're talking about. And we're able to say this despite the fact that we only had measured quantities here. We only have the measured standard deviation, the sample standard deviation that we use to get the estimator, and we have only the sample mean that is our estimator for the population mean in this case. So to summarize, we have this idea of population, and if we know the standard deviation, for example, an instrument with reported specifications, then we can straight away use the Gaussian distribution to construct some sort of confidence interval. But in cases when we don't know the population standard deviation, we only have a sample. In that case, we can still construct a confidence statement about the population, but we're going to use the student's t-distribution and the estimator for the standard deviation in that case. And then this is important. So, we have this table with different numbers of degrees of freedom that we calculated. So what happens for large degrees of freedom, for example, larger than 30? Well, in that case, the student's t-distribution begins to approach the Gaussian. And in that case, you can just use the Gaussian distribution anyway. So that's convenient. And just to kind of, recap things, you have estimators. They're an attempt to approximate these population values. And of course, that's what we always care about. We want to know the population value. And we're using experimentation to give us information about it. But those experiments are going to be imperfect, so we need to use estimators. And they're going to be good or bad depending on, their consistency, their level of bias, and how efficiently they estimate the population values. And so some of these estimators are going to be slightly different than the population counterparts. So for example, the variance, you're dividing by n minus 1. So it's just good to know about these. And whenever you're reporting confidence intervals or making these confidence statements using estimators, keep in mind that confidence intervals might not necessarily follow the Gaussian distribution if you're using an estimator. Okay, that's all I had. So thank you. Bye-bye.